Okay, so this next tutorial in the stoichiometry unit is about limiting reactant problems. So the first thing you want to think about is exactly what is a limiting reactant. Well, you know from the word reactant that it's one of the starting materials in the chemical reaction. So it's always going to be on the left of the arrow. And it's the chemical substance that gets completely used up in a chemical reaction. That's what the limiting reactant is. So when you're done with that, when that reaction stops, it stops because that reactant has been completely used up. It's very difficult to run a chemical reaction so that both or all of the reactants are used up perfectly at the same time. There's usually a little bit of one of them left over. So remember the recipe questions that I had? According to the recipe, we needed 8 tablespoons of butter, 2 eggs, 2 cups of chocolate chips to make 2 dozen cookies. But I only had 3 sticks of butter, a dozen eggs, plenty of flour, plenty of sugar, and 5 cups of chocolate chips. So when we used the ratios from the recipe to figure out how many cookies we could make, we realized that we would be able to make 3 dozen cookies because we would run out of chocolate chips after 1.5 recipes was made. So what's left in my kitchen after I'm done? Well, I have the product. I have 3 dozen chocolate chip cookies. And then I have some butter left over. I have some eggs left over. I have some flour and sugar left over, but I don't have any chocolate chips. So that means in this example, the limiting reactant was the chocolate chips. So if you're looking at a chemical equation, you can think of it in a similar way. So here we have the equation for the synthesis of ammonia, NH3, from hydrogen and nitrogen. And so the 2 reactants are nitrogen and hydrogen. And let's say we start with a reaction container that looks like this. It has 6 molecules of hydrogen in it and 2 molecules of nitrogen. So when you first look at that, you might not realize which one is the limiting reactant. We can figure it out using a mole ratio step, but I'm just going to illustrate it with a picture first. So before the reaction starts, we have molecules of nitrogen and molecules of hydrogen separately. And then we heat this container up and we give it a little spark to get the reaction going. And during the reaction, we have ammonia forming. So NH3, NH3. We still have some hydrogen left and we still have some nitrogen left, which is a clue that the reaction is going to continue until it stops. And when the reaction stops, sorry, got to go back one slide here. When the reaction stops, it stops because one of the reactants is used up. And in this case, you can see from the picture here that the reactant that was used up was hydrogen. There's no hydrogen left on the right. There is ammonia, that's the product, and there is nitrogen. And if you look at the quantities, we used up 12 atoms of hydrogen. We started with 12 atoms of hydrogen. We only had to use up 4 atoms of nitrogen to make these 4 ammonia molecules. And we started with 6 atoms of nitrogen. So we have left over 2 atoms of nitrogen in 1 diatomic molecule. So that's what our excess reactant is. So if you look at the questions I have down on the bottom here, it says the limiting reactant in this reaction is used up when the reaction is complete. What is it? And that's the hydrogen, because if you look in this container here on the right, when the reaction stops, there's no hydrogen left. The excess reactant is still in the container when the reaction stops. What is it? That's nitrogen. You can see there's still a little bit of nitrogen left. And what else is in the container after the reaction stops? And that would be the product. Don't forget, when the reaction is over, you've always got your product in the container along with any of the excess reactant. So how do we go about solving the limiting reactant problem? We can look at it theoretically like we just did, but how can we actually calculate how much product will form and what will limit the quantity and how much will be left over when it's done? So this process is the same as the basic stoichiometry problems that you've been practicing. The only difference is you're going to see more than one given quantity, 2, maybe 3 sometimes, depending on how many reactants there are. So you have to treat each one like a separate stoichiometry problem. You pick one product to focus on. That'll be your unknown for all the given quantities. And then you go and just perform the stoichiometry that you've learned. So Here's an example problem that we're going to look at. We have the reaction of solid white phosphorus, which is P4, and oxygen, and the product is solid tetraphosphorus digoxide. So determine the mass of tetraphosphorus digoxide formed if 25 grams of phosphorus and 50 grams of oxygen are combined. So again, you want to think about what are the givens or what's given in this problem. So when we look at the specific quantities, we have 25 grams of phosphorus given and 50 grams of oxygen. And if you look at the chemical equation, both of those substances are on the reactant side. So that should be your clue that this is going to be a limiting reactant problem. What is our unknown? We're being asked to find out about the mass of tetraphosphorus digoxide. So our unknown is the product. How much or what mass of that product are we going to form? So let's look at what the stoichiometry looks like. Well, there's a lot of numbers on this slide, so let's focus on them one at a time. The first given was 25 grams of phosphorus, so we always start with that number. Our first conversion factor is going to be from grams to moles. So it's 1 mole of phosphorus over the molar mass of P4, remember, so we have to take that into account. That's 123.88. The second step is always going to be the mole ratio step, or I should say, if you start with mass, the second step will be the mole ratio step. And these numbers, remember, come from the coefficients in the balanced chemical equation. So in this case, it's pretty easy math because both coefficients are 1. But what's important to remember is that the unknown substance always goes in your numerator, and the substance that you just started with goes in the denominator, and that will ensure that your units cancel out correctly. Then the last step in a 3-step stoichiometry problem is the converting from moles of unknown to mass of unknown. So in order to do that, we take the molar mass of what we're trying to find over 1 mole. So that's going to be a multiplication problem. When you do the math here, 25 divided by 123 times 1 divided by 1, don't have to do that math, it's the same, times 283.76, we get 57.3 grams of tetraphosphorus digoxide. Now that would be if 25 grams of phosphorus was completely used up and that was the only thing that we had to worry about. But we have to also think about the oxygen. So we're given 50 grams of oxygen. So we have to go through the same 3 steps with oxygen. Mass to mole, using the molar mass of oxygen, the mole ratio from the balanced chemical equation. Notice how the numerator here is the same as we did for the first one, because we're focusing on the same unknown for any limiting reactant problem that we do. We want to make sure we're consistent with the unknown that we're trying to find. So when we're done, we can compare apples to apples, or we're comparing grams of the same substance to grams of the same substance. Otherwise, we can't really answer the question. So the mole ratio will be the same unknown over the other given, moles of the other given. In this case, the coefficient is 5 in this chemical equation. And then we convert that number of moles to mass using the molar mass of the unknown substance. So when we do the math here, we see that we get 88.7 grams of tetraphosphorus digoxide. But we can't make both of these. We don't add them up, because one of these is going to get used up first. And you can see from the smaller amount of product that the phosphorus is going to get used up first. So we cross out that larger quantity. We don't use that number. You always want to pick the smaller amount of product for the answer to the question. Remember, the original question was, what mass of tetraphosphorus digoxide will we form? And the limiting reactant is the substance that resulted in that smaller mass. So in this case, our limiting reactant is the 25 grams of phosphorus. All right, and there's one other question you might be asked about with a limiting reactant problem. You might be asked to determine the amount of the excess reactant left over. If you get a question like that, you always want to go back to the limiting reactant and start with that. Okay, so 25 grams of phosphorus, same first step, convert to moles. Now the second step is going to be the mole ratio of the other reactant over the limiting reactant, because we're trying to find out how much oxygen is used up. So we have to do the stoichiometry relative to the other reactant. Once we know the moles of oxygen, then we can convert to mass of oxygen using the molar mass. And we can see that 32.3 grams of oxygen are going to be used up. But remember, we started with 50 grams, so we have to subtract the 32.3 grams from that, and we're left with, sorry about that, we are left with 17.7 grams of oxygen left over. So that's your basic process for a limiting reactant problem, and you're going to see some practice problems coming up next.